Well, greetings, mathletes, and welcome back. We're going to be talking about a pretty specific topic today. The topic is partial fraction decomposition. All right, it has that big old name, but the idea of partial fraction decomposition is if you have a rational expression that's all one fraction, there are actually several different times in calculus. And actually, it could pop up in a lot of different areas when it would be nice to be able to split that up into two separate rational expressions with specific properties. And so that's really what we're trying to do today. But it does get kind of complicated. None of the individual pieces of this are actually anything outside of your tool set, but there's a lot of steps to these. Okay, so actually, one of the big concerns I had with this lecture is being able to finish an entire problem on one screen. So, um, like I said, there's a lot to these, but the idea is not overly complicated. It's just a matter of seeing the idea underneath all the layers of algebra that are in there. So, without any further ado, let's go ahead and get started here and see what I'm talking about. Okay, so I just found the setting where I could hide the toolbar, or at least scoot it over out of my way so we'll have a little bit more room. So I think we're going to get everything on here. All right. Um, so to start off with, let's start with our first example. Let's say I have 11x minus 10 over x minus 2. Oof. Let's try that again. Try to make that look decent here. So we got x minus 2 times x plus 1. Now, I went ahead and factored this denominator ahead of time because I didn't want to get caught up in the factoring, but normally that would be multiplied out and you would have to factor the denominator. So here's the idea. Once you have the factors, right, I have two factors. I have x minus 2 and x plus 1. What we're going to do is write these in the denominators. Right, because the goal here is to split this up into two fractions. And you want to split it up in such a way so each of the denominators is one of the factors of your original problem, right? So basically, what we're really doing is normally when you add two fractions together, you have to find a common denominator. We are kind of undoing that common denominator process is what we're actually going to do here. But anyways, we don't know what these two new numerators are, so we're just going to give them, we're just going to assign variables to them. Typically, it's capital A and capital B. If you happen to have a third factor, the next one would be capital C, then capital D, and it just kind of moves on from there. In any case, we have to figure out what A and B are to make this work. Okay, so this is what we end up doing. So we start off by looking at this as one equation. And the common denominator of this equation would be x minus 2 and x plus 1. So if we multiply everyone by the common denominator, so we're going to multiply by x minus 2, and x plus 1. And we're going to do that with every term. X minus 2, come on, x plus 1, there we go. And then x minus 2, x plus 1. So as you do these, you won't have to write this in every single time because you're going to start to see the patterns as they go here. What's going to cancel out and what's not. Once you start to see the patterns, you don't need to write this every single time. But let's see what happens here. So these two factors will cancel with these two. That will cancel with that. And x plus 1 cancels with x plus 1. And we haven't done anything illegal because all we did was multiply by the common denominator. Okay, so with that whole denominator gone, this is now 11x minus 10 is equal to a times x plus 1 plus b, right, b times x minus 2. Okay, so the goal is to get these two polynomials to match up. So this is one polynomial, this is another one. I got to see what 11 is equal to, and I have to see what 10 is equal to. So what I need to do is I need to distribute this and group these by like terms. So that's what my next few steps are going to be. I'm just going to be working on the right-hand side of this. So I'm going to distribute the A, and then distribute the B, and then rearrange the terms so the terms with X are together. And then the constant terms are together. So plus A minus 2B. Yeah, there we go. We don't have any X's or anything. Now, from here, what we're going to do is we're going to factor out the X. So this is now A plus B times X. So A and B are numbers, right? And so A plus B is the coefficient of X. And then over here, these are just numbers. So this is actually my constant term. These A minus 2B, these two terms together make my constant term. Well, if this is actually equal to 11x minus 10, what that means is that 11 has to be equal to that because they both have coefficients of x, right? So that means that A plus B is equal to 11. And then over here, this negative 10, right? 11 has to be equal to A plus B. The negative 10 has to be equal to A minus 2B. Okay, so now I have a system of equations. I have A plus B equals 11, and I have A minus 2B is equal to negative 10. Okay, so what we have to do is take this and solve this system for A and B. And there's different ways you can do it. Most of these systems are going to be set up so that you could very easily solve it by substitution. Most of them you can solve them very quickly by addition. And it doesn't really matter which one you use because once you figure out A or B, whichever one's first, you can just plug it into one of these equations for the last number. Okay, so let's see here. How do we want to do this? Let's do it this way. I'm going to take this and I'm going to multiply the denominator by the second equation by negative 2. So we have, actually, no, not by negative 2, by negative 1. Sorry, I was thinking the wrong way. So the top equation doesn't change. A plus B equals 11. We're going to multiply the bottom equation by negative 1. And this last one should be positive 10 now. And so if we add these together, A plus negative A cancels out. I get 3B here is equal to 21. And then from there, if I divide by 3, I get that B is equal to 7. Okay, so we have our first entry, right? We have B is 7. That is not, the values of A and B are not your final answer, by the way. It is part of your final answer, but it's not the whole thing. You do need to find them to be able to write your final answer. Okay, so B is 7, and we know that A plus B is equal to 11 from right here. So all I have to do is put B in there. So A plus 7 is equal to 11, which means that A is equal to 4. Okay, so we have values for A and B. That, like I said, that is not your final answer. What we were trying to do is break this thing apart so that the denominators of the new fractions are the factors of the denominator of the old fraction. So what we can say now that we know what A is equal to 4 is just plug an A in here. So this is 4 over x minus 2 plus, let's see, what was B? B was 7. 7 over x plus 1. Right? So these do tend to be kind of tedious as far as that goes. But this is your final answer, right? This is the thing you want, particularly the right-hand side of this. So once you have your original problem, you know that these two factors are going to be your two denominators, right? you're going to put in constants for the numerator so that you can try to figure out what those constants are. Then you multiply everyone through by the common denominator so you can clear out all the denominators. Now, the results you're going to have to massage a little bit until you can collect all the like terms together and then factor out the variable part. Right? So anything that's being multiplied by x has to be equal to the coefficient of x. Any constants like these have to be equal to the constant in the equation. And then from there, it's just a matter of solving the system of equations. And you can solve that in a number of ways. In fact, I might take some liberties, so I use more than one method as we go through, just so you can see things. Okay, so that's our first example. Now, the next one is very similar, although the answer comes out looking a little bit different. Okay, so what I want to do is write the problem down. Let's see, I got my pen. Is this on? Nope, it's not. Let's do this again. There we go. Okay, so the problem is this. 7x minus 4 over x squared minus x minus 12. Now you notice the big difference in here is that this denominator is not factored now, right? So the first step you're going to want to do is to factor that denominator to figure out what your two denominators have to be, right? Okay, and you should have one fraction, at least one you should have one fraction for every factor of the denominator. So go ahead and pause it here and see what you can do. See if you can walk through it. It's very similar to the previous example, although I will tell you that the answers you get happen to be fractions in this case. Okay, so I'm assuming you've paused it at this point. Now, the first thing we're going to have to do is factor this denominator. So we can see that this is 7x minus 4 over, let's see, it'd be x minus 4, x plus 3. So what that means is what we're looking for, one of our denominators needs to be x minus 4, and the other needs to be x plus 3, because those are our two factors. And then we're going to give an a and a b here. All right, now we're going to multiply by the common denominator, which in this case, I'm just going to write it one time because we know it's going to go across the whole thing, right? Oh, that looks like an exponent. Well, it's not an exponent. I usually write this on the left-hand side, so it doesn't look like an exponent. But we know that's not an exponent. This is being multiplied by that, all the way across. So this side is going to be 7x minus 4. Over here, the x minus 4 will cancel out, so I'll have a times x plus 3. And then over here, the x plus 3 will cancel out, so I have an x minus 4 plus b times x minus 4. Okay, so we've cleared the denominators, and now we need to distribute and collect our like terms so we can make our system of equations. So this is going to be ax plus 3a, just distributing that, and then distributing the b gives me bx minus 4b. And if I recollect these things, I have a plus b times x plus 3a minus 4b for my constant. And that's equal to 7x minus 4. So that means this has to be equal to 7 because it's also the coefficient of x. So that's our first thing. So we have a plus b equals 7. And then over here, 3a minus 4b, is that right? Yeah, that's 3a minus 4b has to be equal to negative 4. Okay, so this is our new system. This is our new system now. So we need to solve this system. And just for variety, I'm going to go ahead and, last time I used used addition to solve the equation by multiplying one of them by a negative. And I could certainly do this. I could multiply the top by 4 and add it to eliminate B and solve for A. But I'm going to use substitution just to remind you what it looks like. So here I can say that if I subtract B over, A is equal to 7 minus B, which means that anywhere I see an A in the other equation, I can replace it with 7 minus B. And I have one right there. So it's 3 times 7 minus B minus 4B is equal to negative 4. And then distributing and collecting like terms, this gives me 21 minus 7B. I collected the like terms at the same time, is equal to negative 4. And subtracting that over and dividing by negative 7 gives me that B is equal to 25 sevenths. Okay, so we have B as 25 sevenths. Like I said, it is a fraction. So now we need to find A. Well, we already know A is 7 minus B, and we know what B is. Right, so this is our first constant that we needed. The other one, A, is 7 minus B, and since that's B, this is now 7 minus 25 sevenths. 7 is 49 sevenths. So that gives me 24 sevenths. Right? Now, I should have condensed that a little bit better. I need some room. Where do we want to put it? I'll just put it down here. Okay, so since we know A is 24 sevenths and B is 25 sevenths, that means that we can write this expression here with the fractions in place. So if A is 24 sevenths, this is, let me switch colors so it stands out. This would be 24 sevenths over x minus 4 plus 25 sevenths over x plus 3. Now, it's typically not written like that with the fractions in the numerator. And one of the things you could do, if you have a fraction and you divide it by something else, what you can do is just put parentheses around it and just multiply it by whatever the denominator is. You can verify this by multiplying by the reciprocal, however you want to look at it. But this does boil down to 24 over, you see the 24 sevenths there, x minus 4 plus 25 over 7 times x plus 3. Right, so it also gets written this way. And so we have our answer. And so once again, I just kind of want to talk through the process we had. So we started out here. We realized we needed to factor that denominator if we're going to get anywhere. So we factored it. We get this. And now that I have two factors. So those are going to be the denominators of my two fractions, right? I'm going to have one fraction for each factor. I set the numerators equal to some unknown, right? And now I'm going to solve. So I multiply by the common denominator to get a more, a fractionless equation, right? I sit there and rearrange the terms so that I have like terms together. And then once I do that, I have a term that is the coefficient of x, which has to be equal to the coefficient of x here. And then I have a constant term that needs to be equal to the constant term over here. And so I set those equal to each other to form this system. And then I solve the system to find A and to find B. So that was a lot, right? But you need to be thinking about what your overarching process is. If you try to remember this by remembering every little step, it's never going to happen because there's too many steps. You have to kind of remember it as a series of goals that you're shooting for. So, however you need to organize that in your mind, that's how you want to chunk this into separate processes and then give a name to each process that you're going through. Okay, so that's two examples, right? And we're going to look at a third now. And the third one um, is actually going to have three factors in the denominator. And and I'm going to step out for just a second before we start um, this last this last fraction. Um, there are actually a couple of other cases that we're not looking at in this lecture for partial fraction decomposition. Uh, one of the try that again. One of the situations that we're not looking at today that we are going to look at in the next lecture is what happens when you have a factor that shows up more than once in the denominator. Like if you have if you factor the denominator and you find out that it's actually x plus 1 times x plus 1, you have to handle that differently than you would handle than you would handle it if they were completely different factors. So we aren't finishing this up. We're actually looking at what happens with linear factors that only show up once right now. And then we're going once we get used to that, then we'll take a look at the more complicated cases. So okay, so let's get back to the example. All right, so the last example here. Oh, let's get to the page that has my last example on it. Looks like this. We got. This always works better with the pen on. There we go. 4x squared minus 5x minus 15 over x times x plus 1 times x minus 5. Okay, so we have three factors of the denominator now, but they are all distinct factors, so we don't have to do anything special. But we do end up with three different fractions that we're breaking it up into. So the first one would be a over x, because x is my first factor. The next one would be b over x plus 1, and then c over x minus 5. So we have three things to find now, which means that the system we're going to deal with is going to be a 3 by 3 system. So we're going to have three equations, we're going to have three unknowns. So it's a little bit more work to get through these. Okay, so same process. We're going to multiply by this common denominator all the way across. Okay, so how do I want to write that? Let's do it this way. I'm gonna do the same fudgy thing that I did last time. Just so I have it there for reference. Okay, so this whole denominator will cancel. So we got 4x squared minus 5x minus 15 is equal to, well, here the x will cancel. So it's a times x plus 1 times x minus 5. And then here the x plus 1 cancels. So this is plus b times x minus 5. And then here the x minus 5 cancels. So this is c times x plus 1. You notice each one of these lists of factors here is just missing. It's missing whatever the denominator was. So that's a good way to actually be able to write it out. That's one of those shortcuts you can get a hold of. Once you do a few, you can see where it comes from. Okay, now, so we're going to have to multiply all this stuff out. We're going to have to collect our like terms together and then form our system. So multiplying this out, it would be a times x squared, and then that's 1x minus 5x, so it's minus 4x minus 5, and then plus, well, we can just distribute this, b times x squared minus 5x plus, let's try that again, c times x squared plus x, right? Okay, so we have, if I distribute everybody, I have ax squared minus 4ax minus 5a. Here I have plus bx squared minus 5bx, and then here plus cx squared plus cx. Woo! Boy, it's a lot of work. Okay, so let's start by, looks like the highest exponent I have in here is x squared, so we'll collect those together first. So I have a, b, and c as coefficients of x squared. So I'm factoring at the same time here. Okay, so that's this term, and this term. And then next up, I need the terms with x's in them. Okay, so I have, let's see here. So plus, see, I have minus 4a. That's for this one. That's done. Minus 5b. That's for that one. That's done. Plus c. And all of those were x's. And now I need my constant term, and I've used all these up here, so all I have for my constant is now minus 5a. Whew, boy, that's some work there. So now let's set this equal. So 4x squared minus 5x minus 15. All right. Now, so I want to point this out. Since this is an x squared and this is an x squared, that means the 4 has to be equal to this. So that's the first step in our equation. A plus b plus c is equal to 4. Now, next one up, I need coefficient of x equal to negative 5. It takes all of that to be a coefficient of x and equal negative 5. So the next one is minus 4a minus 5b plus c is equal to negative 5. Okay, now, last one. I have negative 15, and that's the only thing I have. This is the only constant term I have left, which means that negative 5a is equal to negative 15. Okay, so this is actually my new system. Hold on a second. There. Okay. So this is actually my new system, this thing right here. And so I have to solve this. Now, this is a big system. It's a 3x3 system. It takes a little bit more work. So what I am going to do is I'm going to erase this, right? We already have the results from this. All we have to do now is get a hold of the actual equations. So I'm going to take this out of here just to make room. Okay. Now, so we have, let me turn that back on. So let me rewrite the system. A plus b plus c equals 4. Negative 4a minus 5b plus c equals negative 5. And negative 5a equals negative 15. All right. So let's go ahead and get rid of that. There we go. So let's get busy with this. Now, there's different ways you can do this, but most of these are going to work out kind of nice. This right here only has one variable in it, and this tells me right off the bat that a is equal to 3. So if I know a is equal to 3, I can change all of these equations by substituting 3 in for a, right? So I'm not even going to use this third one other than the substitution. So that means that I have 3 plus b plus c equals 4. And if I plug it in here, I have negative 12 minus 5b plus c is equal to negative 5. right? So let's move the 3 and the 12 over. So we'll have something that looks a little nicer. So I have b plus c, and if I subtract 3 over, I get 1. And if I add 12 over here, I get negative 5b plus c is equal to 7. Okay, well, we can use this to solve this. Let's just see what we got here. So I'm going to start, I think I'm just going to multiply the top by negative 1. And so that gives me a new system that gives me negative b minus c equals negative 1. And then the other equation stays the same. So it's negative 5b plus c is equal to 7. And if I add those together, this dies, right? And I get negative 6b is equal to 6, which tells me that b is 1. So that's actually very convenient. Okay, so if b is 1, and we come up here, we know that b plus c equals 1, which means, well, if b plus c equals 1 and b is 1, c is 0. So now c is equal to 0. So we have two of them. I didn't even know one of those could be equal to 0. We're going to actually have to check this out. Okay, and so that's that. We got c is 0. Now, if b is 1 and c is 0, we know that a plus b plus c is equal to 4. So that means that a plus 1 plus, that's b, plus c, which is 0, is equal to 4, which tells me that a has to equal 3. Right, so really it's just a matter of putting things together now. And I just noticed something too. I apparently can't do division correctly. Thankfully, this mistake was towards the end. I just noticed this. That, okay, could I have my pen on. If I divide 6 by negative 6, I get negative 1, not 1. So let's go back and look at that. So that what that means is that B and C are incorrect. I need to go back and plug this in again. C is not 0. In fact, let's write that in there the right way. Okay, so this is negative 1. Now, if B plus C equals 1, and B is negative 1, that means C is 2, not 0. The C coming out 0 raised my eyebrow, because the only way that could happen is if the original problem wasn't reduced. So C is now 2, so B is negative 1, C is 2. Now we can go back to A plus B plus C, there we go, equals 4. Sorry about that mistake. So A minus 1 plus 2 equals 4. That means A is 3. Wait, that's the same result we got before. Oh, that's weird. Okay, so A is 3, C is 2, and B is negative 1. So all we have to do now is put them in here. So what that means is that my final answer, oops, there we go, is this. So A is 3, so this is 3 over x plus, and then let's see, B is 2. This is now 2 over x plus 1. And then C, wait a minute. C is 2. Well, I'm losing my mind here today, guys. I'm apologizing for my insanity. So that's a negative 1. There we go. B is negative 1. And C is 2. And that goes with the x minus 5. There we go. right? And if you wanted to, you can move this out and make this a subtraction. So this is just minus 1 over x plus 1. But you have it broken down into three fractions so that the denominator of each fraction is a factor of the original denominator, right? And that's a very specific set of circumstances that you're trying to keep there. It turns out it really helps for a particular task when you get into calculus. So that's really why you end up learning this in the first place. In fact, it doesn't really show up until the second semester of calculus, but it's still a very useful tool to be able to split these fractions up over their over the factors of their denominators. And in any case, that is the skill that you need to acquire with this lesson. When we come back to the next one, we're going to look at the other cases. What happens when you have a factor that looks like x plus 1 squared? Or what happens if you have something that doesn't factor, like or only partly factors? Like you can factor an x out of this, but you still end up with a quadratic factor that won't break up any further. So we'll be taking a look at those in the next one. So practice these for now. They do take some time, so be patient with yourself, and just concentrate on the arithmetic. Remember what your big goals are, right? To the first goal is to just get the coefficients lined up, and then you get your system, then you solve your system, right? That's the strategy for the whole business. Okay, so until next time, keep your pencils and your wits sharp.